Hello and welcome to Rivers Design's webinar on designing memory controllers for DDR5 and HBM2.0. I'm your host Deepak Shankar, and for the next 45 minutes, I'll be going through a few introductory information about DDR5's, HBM's, memory controllers, and then walk through how you can try to optimize the architecture of your memory controller based on your application, your workload, your traffic, your fabric configuration, and a variety of other attributes. Before I get started, there's a couple of things that I wanted to do some housekeeping. First and foremost is all attendees are placed in mute. If you want to ask a question, right in Zoom at the bottom, there's a chat button. You can click on that one, and then it'll open up a group chat window, and you can either send a message which everybody can view, or you can just have send it only to the host, that's myself. So with this, I would like to get started. So today we've got quite a bit of agenda for the 45 minutes, but we're trying to cover as much a space that you get a feel for how do you really design a memory controller. A quick introduction to HBM2.0 versus DDR5. HBM, as all of you know, is a memory interface that resides in the stack of your processor or your SoC, while the DDR5 is an off-chip, sometimes even on a separate board in your particular design. HBM is really used where the memory access, the distance or the wire delay to the memory has to be extremely short, like virtual realities, gaming applications such as those. DDR5 is what you find now in a lot of data center designs, with x86 now starting to offer DDR5 type interfaces. Substantial difference between the two. Clock speeds are much higher for DDR5 versus HBM. The HBM cost runs about $175 for a stack of 8, while a significantly higher numbers there for DDR5. The transfer rates are also quite different between the two, and the devices that are used are also quite different, which means the power consumption between the two is also significantly different. Now, before I get started, I just want to show you some of the parameters that are relevant for HBM 2.0 versus a DDR5. With the HBM 2.0, we're looking at, or even with HBM, you're looking at the address ranges, the bank groups per channel, because that determines whether you're 2.0 or whether you're regular, the timing, and the bus width, of course. In the case of a DDR5, which as you know has 2 channels, so there's the buffer sizing for the channel, there's a burst length, and whether you want a same bank refresh or bank to bank refresh. So you have the refresh that is kind of alternate, because now with DDR5, there are certain substantial differences compared to DDR3 and 4, which are what I used in HBM 2.0. Now, memory controller as a definition is something that is a control unit that allows you to communicate between your masters, be it the processor core or an accelerator or a DMA for an interface, to the main memory. Now, memory is a key component design. It's also shared, which means performance can be a major bottleneck. The location of the memory controller is probably one of the most complex elements of your topology design, be it on a NOC or be it on something like an AXI bus or even on a PCIe, depending on what type of design you're involved in. One of the biggest or the main roles of the memory controller is to really decide which request gets access to memory, what duration, and in what order. So be it like, for example, here, one of the comparisons that we did to try to figure out, how much is a real impact of memory controller is where we're having a shared bus connecting the CPUs and memory controller. And the intelligence of the memory controller is where we are going between read to write switching, where we found that it has significantly higher benefit than interleaving across memory ranks. The other one that is of importance is really looking at how you can lower your read latency by delaying the scheduling of your writes. So you have a number of reads that are completed before your writes get started. These are all elements that are part of your memory controller architecture, and all of these have significant design constraints or bandwidth impact. Now, these are what we call the traditional elements of memory controller. In today's memory controllers, there is another key element that occurs. This key element is all about understanding your application, understanding your workload, and providing a solution based on your workload. Now, what are the typical parts of a memory controller? You have an address decoder, a buffer. This is probably the biggest part of the design, with a buffer management, and very complex scheduling algorithm. It can be as simple as a first come, first served with priority, to something a deficit round robin with intelligence for multiple reads before a write. Of course, there are other considerations in terms of channel, which is you want to have separate reads or writes or a single channel for the design. The other piece of it is what are the interfaces to the processor and also to the DRAM. So is the memory controller closer to the processor or closer to the memory? Where does it need to reside? And then, of course, there are other attributes related to signal handling and triggering the refreshes and things like that. Now, one of the key elements when you're designing any system is to really evaluate what are the criteria or what are the analysis that decide your quality of service. So is it things such as, one of the ones very common in memory control is looking at latency versus bandwidth. As you increase the latency, say, of your write, does that increase the bandwidth? Or what is your total latency irrespective of read or write? As you change that, how does it change the bandwidth? Now, memories do consume a lot of power. So really looking at bytes per watt, which is the amount of data you can do a read or write against the watts. That's another significant activity. The other one is the buffer occupancy. More importantly, how long is it staying in the buffer? So that really would have a significant impact on the MIPS on your processor code. Now, algorithm efficiency, so this is your scheduling algorithm in your memory controller, really determines the maximum bandwidth for your target application. So one size fits all never works. It's really about your application, the number of cores or number of accelerators, and how you handle the workload or the request between these different masters. And that's where the algorithm or your scheduler comes into significant play. So these are the elements that really determine what is your memory performance, or what we call the quality of service. Now, looking back at those attributes that you just saw, there are a variety of statistics that are typically looked at. For example, here, obviously the biggest one is really looking at the throughput. So what is for different workloads, different number of masters and slaves, different topologies, what's going to be the throughput through your memory? The other one is really looking at the latency for your read and write request. And then, of course, the big thing is your power consumption, which is the amount of power that you're looking at in terms of both the instantaneous and the average power. By instantaneous, at every point in time, what's going on in all the banks, or what's going on in all the devices in your HBM, and what state they are in. Are they in a refresh state? Are they in active? Are they in a standby? Are they in any other state? Or how many pages are open? All of those determine your power consumption at a point. Now, the other aspect is also looking at what's your average or your cumulative power, because that determines how much of power you want to get from your battery as well. A key aspect which I remember I talked about is really buffer management. And as you can see over here, in this particular design, you can see the buffers increasing the consumption. which also is shown by the amount of latency and the increase in the latency right over here, without a significant increase in the throughput. So obviously you do have a design issue either from a scheduler standpoint or the size of the requests coming in from some of the masters that is causing a pretty large buildup of buffering without increasing your throughput that you're getting from the system. Other secondary statistics are things like, it gives you your stats on your delay for your min-max, mean, and standard deviation, plus, what is your, how many entered, how many rejected, and how many actually exited successfully. Now, one of the things we talked about is, now that you have an introduction of what the memory controller is, what is HBM2.0, what are the DDR5s, let's look at the concept of architecture exploration, because we're really going to blend the two together. One of the key things about architecture exploration is really understand what it is you're doing, because there is so much chatter about architecture exploration and everybody has their own definition. Architecture exploration is really trying to put your entire system model together. It's not just designing hardware. A lot of people talk about performance validation, performance analysis, things like that, where you're really trying to put a hardware feel and try to come up with architecture exploration. That's really not the case. It's really about what is the total? Is bringing in your hardware, bringing your software, bringing your network, putting them all together to form either your system on chip or form your embedded system, and based on that, do an exploration of your system specification. So it can be as simple as scheduling my tasks on a particular core based on the memory access versus just varying the clock speed and seeing how much the maximum clock speed I can handle for the memory controller design that I've already done. Of course, a variety of analysis, including timing, energy, cost, weight, efficiency that need to be considered. Now, there are really three aspects to architecture exploration, which is really performance, power, and functionality. Failure is an important criteria in certain designs, not so important in other designs, but it does form a major role because if you want to provide some sort of security for your system, doing the failure analysis does become a critical aspect. Performance is always timing related, so it's like anything from buffer occupancy to looking at the effective bandwidth or request response or request latency. Power, as we already talked about, can be an instant power, which is at one point in time, what is the total power? Can be just of the DDR or the memory controller, but it can also be for the entire SoC or for your embedded system, because of course the memory controller, the DDR is only a part of your system. So looking at that overall design as well is equally important. Then of course, what is the efficiency or what is the quality, be it your software scheduling or the power consumption based on certain arbitration schemes that you're deploying in the memory, or a very important aspect, which is really buffer management. You want to first come, first serve. You want to reorder based on priority. Do you want to do a last come, first serve? How, if you run out of bandwidth, run out of buffer space, how do you handle the new requests coming in? Or do you handle how the reads and writes have to be organized within this buffer? So the buffer scheduling and arbitration is a major aspect in terms of trying to determine what is going to be your quality or what is going to be your quality of service. Now, as I mentioned earlier, we do have a chat window, so you can feel free to type in your questions, and there are multiple people standing by to answer your questions. So just feel free to ask the questions as they come along. Now, when we look at the analysis, and some of them are already discussed, anything from the buffer, which again, as I mentioned, buffer and power, versus the other attributes. So memory controller design is actually an interesting part because it involves looking at the overall system, not just the memory itself. So it involves looking at the, as I mentioned, the number of masters and the clock rate and the request sizes that they come in. all the way to looking at the credit policy that you can offer in the memory itself, meaning that certain masters can get extra credit, while certain other masters get lower credit, or certain can get a higher priority, others can get lower priority. So it really becomes a management of how the memory accesses are done. Of course, you can even get it down to the type of software. So what's going to be the software task as well is something that you can look at. Now, let's look at an overall performance evaluation of the system. So when you want to put a full system together, there are a lot of attributes that come into play. And I'm not going to go into details on any one of these things. I'm always available after the session to answer any questions. But you can look at, like, for example, the memory itself may go through, in this particular case, it's an XP or an NVIDIA chip, where you have a Vertex or a Kintex 8 that handles all the interfaces. Can be video interfaces, can be mini-bit interfaces, can be analog, any of those kind of things. They come in, they have a local memory map, and then they get uploaded through a DMA, through a PCIe interface to DRAM, right? And then, of course, you have the traditional multi-core GPU display controller. So as you can see, it's a complete infotainment system. So what we're trying to do over here is trying to figure out for different types of algorithms over here, what is going to be the maximum bandwidth that I can get. So as you can see here, it's not just about the SoC, it's not just about the software, not just about the interfaces, it's putting the entire system together, including the power, which is a major attribute in this particular design. So only when you have the entire end-to-end design is when you can actually look at the quality of my particular memory controller algorithm. And of course, a variety of components are required to make this happen. This is one particular example. It does not mean that this is the only way you can describe it, because just the fabric itself, as I mentioned, you can connect it directly to PCIe, or this does not have to be a DDR memory. It could be a SSD or a flash. So there you have a completely different type of memory controller as well to be evaluating. Again, this can be an AXI to a NOC to something that's more proprietary, like a lot of artificial intelligence SoCs have completely proprietary systems as well. Now, let's go back to the memory controller design. Where does the role of architecture exploration fit in? One of the attributes is that depending on the type of design and depending on the available information and depending on where you are in the design process, you might use one of two different types of architecture exploration. It can be a more stochastic or it can be a more cycle active. And I'll be talking about what's the difference between them. Now, when you model, as I was showing you earlier, you have, irrespective of whether it's a stochastic or a cycle active, you still need to worry about the interfaces, the workloads, the traffic, the software, all of those. And of course, the memory controller can be abstracted depending on stochastic or cycle active, but you still need to put in sufficient amount of detail into either of those. Because that is, the memory controller is the key aspect that you're trying to analyze, you're trying to design. As I mentioned, a variety of variations. You can change the scheduling algorithm, you can separate single or dual channel, different buffer sizes, clock speeds, the number of DRAMs connected, like the DDR5 has like 2 channels. So you have those kind of attributes to take advantage, and of course the number of masters. So it's really about generating all those reports and then based on that evaluating the quality of service. So what's the difference between the two? If you look at the parameters to define a memory controller for stochastic versus cycle active, a stochastic can be simple as just a delay function. So you don't have the details of the address decode, like the memory map, all of those kind of things, but rather it takes only cycles to go through the memory controller. Of course, you could have your scheduling algorithm for the buffering, and then you'll have like certain things which are like your memory width and your buffer length, but that's really all you need to start off in defining your memory controller. at a cycle accurate, which is a very, very detailed, almost emulating what the hardware is going to do, you do need inputs that have the exact address. And if you get larger data sizes, you need to be able to fragment them. You need to look at clock speeds. And of course, some things are common, like the buffer lengths, the memory width, things like that. But then here you also have to worry about burst lengths, the timing values that are provided by the vendor, refresh related attributes. All of those kind of things have to be considered. Also here, in the first case, the scheduling algorithm is going to be a little more general, meaning you're only looking at reads versus writes, which page am I going to, or which bank am I going to. Like here, you have to worry about the address, you have to worry about row column. So the details that you put into the scheduling algorithm is an increment over what you do with the stochastic model. Now, when I look at an architecture model that incorporates the memory controller, as I mentioned, there are multiple things to consider. Of course, you have the masters, you have the I heard that some people were having problems with the audio, so I'm going to try to change the location of my audio system so people could hear it better. You got the masters, you have the fabric, of course you have the memory controller and the DRAM, and of course the key aspects are the exploration parameters and the reports or the analysis tools that are part of the design. So I'm going to take a quick break and make sure that you guys are not having too much of a problem with the audio and you're able to follow through. In case additional people are having problems with audio, let me know and I will make sure to increase the volume as well. Okay, so if anybody else is having problems, just let me know and I'll work through the system. Now, I'm going to go ahead and modify, go ahead and go back into a modeling environment. And in the modeling environment, so this is the Visual Sim modeling environment. And the particular design that I'm interested in is similar to what we just saw, which has got multiple traffic generators. It's got the bus, it's got a memory controller and a DRAM. This one here is the cycle accurate version. I'm also going to show you one with the stochastic version. So I'm going to go ahead and click on the Go button. I've already configured these masters, the fabric, and the memory controller as well. And we're going to try to see what the reports look like. Try to understand how we can interpret these. We're going to look at only a few of them. Of course, this one here shows you the AXI bus. In this case, what's going on in the AXI bus. That's of an interest to us. We're going to focus here on this attributes. This one here is statistics about the delays associated with the request, the reads or write request. So we had 631 requests, and you can see what was the effective throughput that we're getting for all of them. This one here kind of breaks it down into, what was the command queue. So notice we hardly had any buffering right over here. It can show you how many reads and writes have been done, and what's the bytes, what's the total megabytes per second. So we got like in this particular case, we got about 1 gig of memory data that were pushing through the model or pushing through the design. Of course, you can always try to increase the traffic and try to see if we can get additional performance. So one of the things we're going to try to do here is try to increase the traffic rate. So rather than making it, I think we'll make it 220 over here, and maybe make this 400. So not all of them are modified. Just one of them is, only 2 of them are modified. We're going to rerun the simulation to try to see if we increase it, which is essentially telling me that I'm going to be putting a faster processor, and it's going to be generating, or a faster core, and it's going to be generating some additional requests through the the system. Now this one shows me that I'm really only going to 2 banks, and that's a bidirectional bus. We're going to take a look at it and see if there was significant thing. Not really. We only had like going from 1011 to 1017. So now what we're going to try to do is try to significantly increase it, whereby we'll increase even the data sizes. So we'll make these a larger, much larger data sizes. So requests are beyond what we normally have. So we'll keep this low. So you notice every one of these can have completely different data sizes, can have completely different cache lines. The DMA or their DMA is completely different measure metrics to be able to see how we can get better performance. So as you can start seeing here, there's a lot more granularity, which means the responses are much closer. You can see now we more than doubled the memory bandwidth right over here. So we went from 1.017 to almost 2.430. So what we're going to do is try to see if we can push this even more. So we'll try for 500. This is 550. So essentially what we're trying to do is trying to see where we can break the system. What is the maximum capacity before the system completely breaks down? And by breakdown, what it means is that either the memory controller starts losing data in its buffer, or the bus is no longer able to handle the workload that is being pushed through. So now you start seeing that we're accessing multiple banks. So it's not, we're going 0246 banks. So we're doing that. And it didn't really significantly increase it. So now let's go and look at what is the cause of it. And let's look at the AXI bus, which in this case is the fabric. And what you're going to find over here is some of these masters had an overflow, which means that even though I had this high bandwidth that I'm trying to send through, some of them just couldn't handle the interface. The interface could not handle the workload as yet. And as a result of which, your effective bandwidth is actually starting to drop off. And you can also see that the buffers on the AXI bus, that also has started increasing. We've got like the reads have gone up to 8 here. A couple of things I can try to do experiments with. For example, I can make the size 32, both of them, and which means essentially, like I'm allowing for more buffering of data, which means I can handle a much larger load, and try to see whether that increases. So notice that we're not just changing the memory controller, parameters, but also trying to change other attributes, which are like your workloads, your AXI buses, and things like that, and try to see if we can, get better performance. Matter of fact, when I increased that, the buffering on the AXI bus, the bandwidth just went down. So essentially, that means that just because I, provide more bandwidth on the AXI bus does not mean that I'm necessarily going to get better performance on my memory controller. Of course, there are other attributes you can change. For example, I can increase the buffer size on my memory controller. I can, I can make it like 64 buffer positions of memory width, which in this case is the parameter at this level. Memory width is 4 bytes. So I can make the 60, and then I can say commands in a row, which is how many reads before I got to jump over the right. I can do that 12. And of course, I can change the memory width to make that 16 as well. So now what we're doing is starting to change the memory controller. Until now, we were trying to see with the existing architecture that we had, how much more can we handle. Now, we're making the memory controller significantly faster, trying to see if we can get better performance there. Also, we're changing the scheduling in this case to, add more reads to show up before I jump over to a write. So now trying to see how that changes the performance. Now, in fact, you see absolutely no change in the performance as a result of doing that. And you can see that even though I increased that read-write thresholds, there was really no change over there. So as a matter of fact, I didn't actually get more performance as a result of making a lot of changes into the memory controller. So which means that I not only have to evaluate if I want higher bandwidth, which in this case, I got a 1333 times 4 bytes, which means I've got about 10 and a half to 11 gig of memory, but in reality, I'm only getting about 2.5 gig of memory. Now, another attribute to also be looking at is the controller, which is the bus, is only 1200. So we can try changing that to make that 1600 and try to see if we can possibly push more data through to the memory controller. But that's another option that we have available in the design here. Also, if you notice the making changes here is rapid and pretty fast. That's one of the advantages of architecture exploration, is the fact that it allows you to try a lot more experiments without having to invest in a prototype board or trying to write up software and connect your ARM or your DSP or your GPU to the system. You can just do a more parametric changes and try to see what happens in the system. So one of the things I'm going to look over here as well is, So there's also additional things I can do to try different experiments, like changing my, my refresh rates and looking at those attributes as well, and trying to see if I'm going to get better performance. Of course, I can change the burst length as well and see how that will affect the system. So in a sense, I can try out a variety of experiments, not just on the controller algorithm, but other attributes to try to see if I can improve the performance. Now, as you saw here, the memory controller for a stochastic versus cycle accurate is fairly different. In this case, you're focusing on the access times, and the controller is simply just a delay. While in this particular case, you're looking at the address mapping, the command buffer, the commands in a row, burst length, and such other attributes. Of course, the timing as well. So if you got to move the cycle accurate, you have to put in a significant effort over and above what you see with the stochastic model. Does that really mean that the stochastic model is not as accurate? Not really. It's more a function of the time you have, the amount of data available. In this case, on the right-hand side, you really need the addresses. If you don't have the addresses, this is a better option. So if I go back into a model that does not use the cycle accurate, but uses more of an abstract, if I open up here to the DRAM, you can actually see that these are the attributes associated with that one. So now a similar design, but now here, not only am I looking at the hardware, I've also incorporated the details of the software. So this one here is the application running on an on an ARM processor. So now, rather than just doing, like, here's my hardware and my hardware is generating so many requests and things like that, I'm now incorporating a real workload, a real application onto my processor. And I want to see what the performance is going to be for that particular system. So here now, I'm not going to focus on a lot of other attributes, just focus on a couple of them. But one of them that I'm going to focus on is the memory utilization. Notice here you can see what the utilization. This particular case, there's only one core. We have a pretty high performance memory, so not a lot of usage. But you can actually see what the different types of memory are. You can see what the throughput is and how each device. So this is another interesting thing. In this case, we only have one master. You can see how much of memory is used by that single device. Now, when I go back to here, what I can do is I can add another device. In this case, I'm going to add a hardware accelerator. So this device here is now connected here where the rest of the system goes into the ARM subsystem. Same design, but now I'm adding accelerators for certain functionalities. So think about it as whether it's an MPEG in this case or an artificial intelligence in your case. The designs might look extremely different. Here's another one which is interesting, which is really your power consumption. So earlier on, if you notice, it was pretty flat. Now you're going to start seeing some additional changes. And you can also see what the utilizations of my RAMs and ROMs are based, and also how much throughput is based on the addition of the accelerator. So that was a baseline, but now the accelerator has started adding significant bandwidth and significant consumption of my battery power. Now, your eventual goal is the quality of service, which is really about what is it that your application is doing. So in this particular case, the application is really about taking requests coming in and processing it through a series of MTAG activities in a pipeline and then presenting it to a display. So what we want to know is how many matrices can be processed over the period. So in this case, we're running for about 20 milliseconds. How many matrices are handled on average over the period of the simulation? So I want to see what is the quality of my output based on a certain hardware platform with certain memory controller. So in this case, what was different from the earlier design was now I had a real application. I want to see what happens to the real application, and then looking at the hardware, looking at the buses, the memories, and seeing what their performance is going to be, and including all of their performances into this particular design here. And that can tell me what my effective quality of service is over the period of the simulation. Again, as I mentioned, if there are any questions, go ahead and ask them on the chat window, and there are people standing by to answer those questions. Now, one of the attributes that is very critical in the memory controller is really the power. One of the things about power is that your memory does consume significant amount of power, especially on an SoC system. And if you have an HBM, it's even more significant because the HBM power is stacked up within the same die. So the power is a significant part of the design. So at the stochastic level, what we care about is the standby active refresh. But now, when I look at cycle accurate, I have to include the RAS, the RRD, the read write, the acknowledge, and then of course there are other additional items that are not included here, which is like the refresh power, and you can see write to read and all of these attributes as well. So what you're seeing here is that it's no longer about, oh yeah, I've got a delay for my thing, let me put a delay for the power for the memory controller, and then there's a few refreshes once in a while, and there's like read and write. Power is no longer that. It's a significantly more than that attribute. So looking at power, I'm sorry, I picked up the wrong model. But, I'm going to pick up a simpler version of this particular design. So when we look at power, there are a variety of attributes related to power. So for example, if I zoom into this particular region, you can see over time how many devices have been turned on and turned off at every point in time. And as a result of that, how much does my instantaneous power hit? Also, you can see what the average power is. Plus, you can also see for each device, what's the cumulative and average power here. So now it's not just about, okay, just give me a power number, a single number, but rather it's like I'm looking at every point in time, cycle by cycle, what is happening in my design. What I can do from there is I can start expanding the power analysis to also incorporate. I'm going to move into the desktop here. And I'm going to look into here we go. Look into each device, and I can see cumulative and average power is for that particular device. So allows me to look at those aspects of power as well that are beyond what you'd be looking at for a particular design in terms of the sorry, I just ran my train of thought. Give me a second. In terms of the actual power that is being consumed as a single number, now we're starting to look at something where I can see it on a per device. Now, it's also possible to look at power on a per task basis. So if I go back to the design that we were looking at earlier, which was this system model right over here. I might have shut down that system. Never mind. We had a workflow which told me what the sequence in which my applications are targeting the ARM or the hardware accelerator. I can look at what's the power for each of those tasks as well and see what happens in my particular system. Now, what we're going to do is we're going to try, we saw an experiment with something that was just having masters and we were feeding into it. Now what we're going to, and they were all very symmetric, so which means they were essentially like math cores, processor cores. Now what we're going to look at is we're going to look at a design where we're going to have significant differences, which means that I'm going to have different types of devices, so CANs, Ethernets, processors, GPUs, displays, and now look at what my system design looks like in terms of the okay, here we go. So we've got a design over here where we've got traffic generators to emulate the Ethernet, CAN, ARM, GPU, reads and writes, and enable all of these. And for now, in this particular design, we don't have significant details inside the processor or the GPU. We're going to go ahead and run the simulation. And the purpose of doing that is to look at the what you see over here, which is really about the DRAM throughput that we're getting for the for the different devices right over here, which is DRAM used by ARM, CAN, Ethernet. And you can see further, we'll see additional items as well. Of course, you can see what my DRAM utilization is. You can see now, you can see all the devices and see what the powers, what's the throughput that is being utilized by each of the devices. Of course, this now incorporates the DRAM latency, but what it also does is shows me what is my end-to-end. From the time the request came in to complete the request, that's the kind of thing that you're seeing right over here as well now. And then, of course, there are other attributes that you can look at, which is here in this particular case, is for each of the individual devices, how much of power are we, how much of performance are we getting? Now, the key aspect right over here is the fact that all of these devices are essentially workloads that are, traffic that is being generated to emulate the performance. Now, what we're going to do here is we're going to move from that to where we're replacing these. Of course, we got a trigger and enable, like an interrupt. But now we'll replace the internals with like the processors. So in this case, we have the 4 arms with Denver. So this is the Drive PX processor model from NVIDIA. We have local memories. And then, of course, you have the GPU with its own list of like warps and number of PEs and the execution units, the cache buses, all of those attributes as well that you can see right over here. So what is different now is earlier on was the masters were essentially traffic generators that we were emulating the actual behavior of the masters. But now we have decided to actually incorporate the real activity associated with all of them. So now what changes is the fact that now you're going to see not just the memory performance or the memory activity, but you're also going to start seeing, for example, here, the power consumed. Of course, here you can still see the bus latencies and things like those. You can also start seeing the, the activity of the warp. So this here is telling me which warp was active at what time. You can actually see that this is the first part of it, which is the 0 to 250. So essentially, we've got 500 warps. Half of them are allocated for one program, half of them are allocated for another program, and you can see what is happening here. Now, based on the activity that's going on, like for example over here, let me just take this region, which is simple. You have, after this, you notice there's a spike up in terms of the latency, primarily related to the fact that the Ethernet and of course the other Denver are also starting to come in and start playing a role right over here. And of course here you can now start seeing that in this particular case, I had the 251 to 500 warps that are being utilized. So you can now start seeing where I'm no longer using a stochastic, I move to a cyclic. But notice the infrastructure is still identical. What you saw in the earlier model and this one, the infrastructure is just that we swapped out the more stochastic version, which is essentially just a delay, to more of a cyclic, which is the actual behavior of that particular core or that particular system. So for example, if I open the display controller, here, it's now got a DMA block. Earlier on, what we had in the previous design, right over here, is we simply had the request went out to the memory, and when it came back, we just turned it around and sent it out to the display. So it was a simple emulation of the DMA, but here now we have an actual. Here now we have the DMA block. Of course, one of the nice things with this particular design here is I can have one, in this particular case, the traffic is all periodic, which means, I define a rate, and at that rate, data is going to go in. While another design here, I think I shut down that window and bring that back up again, is where I can, describe these more with the range. So, this period of time I have so many requests, then there's nothing happening. Then this period of time I have a request, nothing happening, and so on. So, it gives me the potential of creating a far more complex architecture for my for this particular design here. Meaning that now when I emulate my application, it's not just that periodic. I'm not just like on a regular time period throughout the simulation I'm getting data, but rather here I'm getting data in different range areas or different regions of my design. As I mentioned, anyone having any questions can always ask those questions as part of the chat window, and we'll be happy to answer those questions. Now, as I was mentioning here, the design that we were looking at, which was an infotainment system, we did have the data coming in through a video camera, SRAM, PCIe. So now when I start looking at a design of this kind, so I was initially looking at the memory controller and the SoC, but now I've taken that same SoC, but incorporated a PCIe, incorporated a Xilinx Vertex, and a DMA. So I've now done a board level design. Started with something that was just traffic to a memory, added in all the details of the chip, and then now I have a complete board design that I can evaluate. So as a semiconductor vendor, I can actually look at ways how I could create like a reference design or a prototyping board to try to allow my customers to try different experiments before they actually finally decide to purchase the product. So rather than buying a prototyping board and trying to, load up the software, which probably does not exist, being able to get more of a virtual platform and try to run it against the virtual platform. Now, one of the challenges that always happens in your memory controller design is really trying to figure out where my bottleneck is. How do I determine where the problem is? Remember, we had that initial design where we were looking at, trying to identify for different workloads, for different axis bus definitions, for different memory controllers, what was happening. One of the key things out of architecture exploration to really come up with the best memory controller is to figure out where the bottleneck is, where's the problem, so that I can improve the performance. So, can I improve the latency? Can I improve the buffer usage? Can I look at the throughput? How do I start looking at all of those kind of attributes of my system? And of course, I can modify, the attributes which we did earlier, but really be able to pinpoint. So if you notice, I started increasing the traffic, the bus started dropping data. I increased the bus bandwidth by increasing the clock speed of the bus. I was able to get more throughput. So allows me to look at exactly where is the source of problem. Maybe the memory controller is not the source of the problem. Maybe the problem is somewhere else. So when I look at the full system, allows me to be able to debug and evaluate where the bottleneck is, and then apply the design attributes on that particular area of the design. Not, like just trying to take only the memory controller as an IP block and try to see if I can fix it, but rather looking at the full system and trying to figure out where my problem is and try to solve it. Of course, when I look at a controller, the concept of controller can be expanded beyond just a DRAM or a HBM-based memory controller. So in this case, you can look at doing an NVM controller, optimizing that from queue management, code management, looking at the controller that's associated with the SSD or with the flash itself, and how many of those can I handle at a time, connected to this particular case, the PCIe. So in this case, what we're starting to look at is expand beyond just the DDR and the HBM. We're starting to look in this case as an SSD, because a lot of times in data centers and things like that, you're storing data in SSDs. So you also there as well, you want to have a much faster response time. Allows me to do that. Also, a lot of artificial intelligence systems get their data stored in an SSD. Quick introduction to mirrorless design. We've been around for a long time. We have about over 250 designs that have been done with Visual Sim in a variety of application areas. Anything from building x86 process to multi-core Snapdragons to the Power 10 that just came out, all the way to SSDs, to avionics, to flight control, to network gateways inside a vehicle, to high-performance computers, or even to, as we just saw, infotainment and display systems. So a variety of applications can be done using Visual Sim. Architect, which is the name of our product, and it really is, as you saw, a graphical modeling environment, has a large number of libraries, incorporates your hardware, your software, your network. So it's not just the hardware analysis. Like a lot of times when people say performance analysis, performance validation, what they're really talking about is really the hardware. Here, we can create models of the software, we can define models of the entire system, and then look at what the performance is going to be. Now, architecting these, you can essentially architect any aspect of your system, memory controller, the entire processor, the entire embedded system, or just purely looking at algorithms that are associated with either the integrated or distributed system. One of the key things that we do with Visual Sim is really looking at functional safety. How does a particular design work in the context of a full architecture? Meaning that if I have a failure in one part of the system, does my system still continue to operate, or is it not going to work at all, or it's going to work but does not meet the requirements? Being able to evaluate those very quickly is an important part of the exploration that you do, and that's where Visual Sim provides you the functional and safety analysis. Visual Sim provides you a large library of components, so you can drag and drop any of these components to put together your system. This is an evolving database because almost every month we put out a new IP block that you can utilize for your development. So with this, I would like to thank you for attending this presentation. If you have any questions, feel free to ask them. We are also